Hi everyone. Today I'm going to talk about the revelation gap for pricing from samples. This is a joint work with Yiding Feng and Jason Hartler. First, I'm going to briefly present to you what is mechanism design. So the mechanism design question is to find a mechanism that achieves desirable outcomes for strategic agents. Note that this can actually be viewed as a special case of the multi-party competition in the computer science community. Why? Because this mechanism design question involves different parties. One of the parties is the mechanism, which is also known as the principal, and another party as agents. Okay, and here different parties will have their own data, where for the agents, it's their private preference and their private belief for the environments. And the natural question to ask for this multi-party computation question is who should be doing what part of the computation. A classical solution to the system design is that we should always use decentralized mechanisms, where all parties should do their own computation based on their own information. This is also known as the end-to-end principle. The benefit of using this decentralized design is that usually it will lead to simple mechanisms and that are robust to the environments. Also, this decentralization will help to improve efficiency and reduce the cost of the total system. By contrast, in the mechanism design, we often adopt the solution that only central mechanism should do the computation, which to say that we will focus on the revelation mechanism, while agents are incentivized to report their private preference to the designer, and designer will collect all the information and compute the equilibrium outcome for all the agents. A nice result by Marathon shows that it is actually without loss of generality for us to restrict attention to relation mechanisms. However, although with this nice theoretical observation, we actually observe that non-revelation mechanisms are widely used in practice. For example, people have been used generalized second price auction for the sponsored keyword search, used first price auction in the ad auction, and the all-pay auction in designing cross-sorting context. So, what is the reason why we often observe the non-revelation mechanism in practice? Today, in this talk, we will provide a justification for this by looking at it in the lens of prior-independent analysis. In this analytical framework, we assume that the designer will not have the prior information about the type distribution of the agents, while we remain the assumption that agents will have common knowledge about the type distributions. In this prior-independent framework, the goal of the designer is try to find a mechanism that approximates the Bayesian optimum over the worst-case distributions. Note that we can easily verify the revelation principle will fail in this prior-independent analysis. The main reason is that the designer lacks the prior information to implement the agency equilibrium strategies, even if the designer can elicit those private preferences from the agents. So now that we have seen that actually there may exist some non-revelation mechanism that cannot be implemented as revelation mechanisms, but do they actually perform better, and how much better does they perform? A very nice paper by my two co-authors proposed the notion of revelation gap, which is defined as the gap between the prior-independent approximation ratio of the optimal revelation mechanism and the optimal non-revelation mechanism. I will talk about its formal definition later in the talk. So in their paper, they also show that this revelation gap actually exists, which is bounded between 1.013 and E for the welfare maximization problem, where agents have budget constraints. So this shows that actually non-revelation mechanisms do perform better than revelation mechanisms. The next question to ask is how general is this observation? Does this gap exist for other settings? And does it exist for other objectives like revenue maximization? Our paper provides affirmative answer to those questions. Here is our main result. We show that in the single agent auction, when the seller only have access to a single sample, for the revenue maximization problem, the revelation gap exists for both the arbitrary distributions and the regular distributions. And we provide both upper bound and lower bound on the revelation gaps. So this is our main result. And along the line, we provide a very nice technical contribution, which is providing a framework for analyzing non-revelation mechanisms. This is done by adopting ideas from revenue curves, which is widely used for analyzing revelation mechanisms. This is particularly useful for future studies if people are interested in analyzing non-revelation mechanisms. Next, I will move to the formal model of our paper. We were interested in the single item auction where there is only a single agent. The goal of the designer is to maximize the revenue. The valuation V is drawn from distribution F. We assume that the agent knows both the valuation and the distribution F. The seller can commit to a mechanism, which first lists the bid B, and then the sample is realized according to the valuation distribution. Then the mechanism will determine the allocation as payment according to the bid and the realized sample. We use X of B and P of B as the expected allocation payment. And given the mechanism, for any best response strategy sigma of the agent, we can correspondingly define the interim allocation payment as X of V and P of V, which is defined as the allocation payment for agents with value V when he is best responding according to strategy sigma. And we assume the agent will have linear utility and the mechanism is individually rational if the utility of the agent is always non-negative. Finally, we use M of F as the expected payment of the agent, which is also the revenue of the seller. So this is our model, and we will start analysis with the Bayesian optimal mechanism. So the Bayesian optimal mechanism is the mechanism that maximizes the expected revenue once the mechanism actually knows the valuation distribution F. And Marathon told us that actually the Bayesian optimal mechanism in the single item auction setting is quite simple. It's just posting a price to the agent. Next, we move to the price-independent analysis. We can define the price-independent approximation ratio for a particular mechanism M and a family of distributions F. It is defined as the ratio between the optimal revenue and the expected revenue of mechanism M, while the supremum is taking over distributions over any distribution within the family of F. Correspondingly, we can define the price-independent approximation ratio with respect to a family of mechanisms, which is defined as the infimum ratio for any mechanism within this family. And a little more notations, we use M of R as the set of revelation mechanisms, and M of A as the set of all possible mechanisms, which including non-revelation mechanisms. And we define the revelation gap as the ratio between the price-independent approximation ratio of all possible mechanisms and the price-independent approximation ratio for all revelation mechanisms. So this is a formal definition of the revelation gap. To bound this, we need to have a bound on both the price-independent approximation ratio of the all possible mechanisms and the revelation mechanisms. And that's what we will do for the rest of the talk. We will first start with the non-regression mechanism. The mechanism that are particularly interesting to us is the following, what we call the sample bid mechanism, which is parameterized by alpha, which is strictly positive. This mechanism will first solicit a non-negative bid from the agent, and then the seller will charge the agent alpha times the minimum between the bid and the realized sample. Note that this amount is charged regardless of the allocation, so it's kind of like the OPE format. Finally, the item is allocated to the agent if his bid is at least the realized sample. Note that our sample bid mechanism actually shares similar format as the BDM method in experimental economics for measuring how agents perceive risk in the environment. So it's conceivable that our simple mechanism actually have practical implications, and people can actually adopt this in practice for better performance. And one remark is that actually this sample bid mechanism satisfies the individual rational constraint. The reason is that for any agent, regardless of his valuation, the utility of bidding zero is always there because he will win nothing and pays nothing. So what is the performance of the sample bid mechanism? We will start with a simple case of MHR distributions, where MHR means that the hazard rate is always non-decreasing. So why this is a simple case? This is because the bidding behavior of the agent is actually quite simple. It's binary in this MHR situation. So the bid will either be zero or plus infinity. Why? This is because we can write the expected utility of the agent as a function of the bid. And when the valuation distribution is MHR, this function is convex in the bid. So in order for the agent to maximize his utility, he will find it optimal to use bid as the boundary of the bidding space, which is either zero or plus infinity. Note that if the agent chooses to bid plus infinity, he will win the item for sure and pays the sample times alpha, which is actually equivalent to pay alpha times the expected value of the distribution of f. So our mechanism become outcome equivalent to posting price, which is alpha times the expected value to the agent. Note that the latter is a simple price posting mechanism, which is easier to analyze. And so we will compare to this with the auto mechanism by fine-tuning the parameter, which is setting alpha to 0.82. We can actually show that for MHR distributions, the prior-independent approximation ratio of the sample bid mechanism is at most 1.296. So this is not a large prior-independent approximation ratio, so it means that the sample bid mechanism performs very well for MHR distributions in the prior-independent analysis. Next, we will move to the more complicated regular situations, where the bidding behavior of the agent is actually quite complicated. We will use the method of revenue curves, which is widely used in the literature for revelation mechanisms. To define revenue curves, we need to first define the quantile, which is the probability such that it will exceed the value v in distribution f. And we can define the value v of q as the value corresponding to quantile q in the distribution f. Then the revenue curve p of q is just defined as the revenue from posterior price v of q, which sells the item with exactly equal to q. And note that for any valuation distribution, it can be uniquely pinned out by the revenue curve. And as you can see why it's widely used for revelation mechanism, this is because for any change we make on the revenue curve, it has a very direct effect on the revenue that can be received by the seller. And this is particularly helpful in the analysis. And note that we can define the regularity based on the revenue curve. It just means that the revenue curve was going to be concave. And the main approach in the regular case is to adopt this revenue curve to show the prior independent approximation ratio. Of course, there will be certain challenges in the analysis. The main challenge is that when we change the revenue curve, it will also affect the equilibrium behavior of the agent. Note that this change of behavior will not be present for revelation mechanisms, but it is crucial for non-revelation mechanisms. And this change of behavior will have a direct effect on the revenue of the seller, and the combined effects on changing the revenue curve that leads to change of revenue is usually hard to quantify for non-revelation mechanisms. But fortunately for us, our sample band mechanism have a very simple format, so there are certain properties that we can exploit to make the analysis easier. First, we will have the bit monotonicity, which to say that the optimal bit is non-decreasing in the value, and we will also have payment monotonicity, which is to say that the expected payment will be non-decreasing in the bit. And note that these are general properties for the sample band mechanism. It does not require anything on the regularity. Okay, due to the lack of time, I will not talk about the detail of the proof, but just focus on the main ideas. The main approach we will adopt is just trying to adjust the revenue curve such that the following two holds. First, we will try to preserve the Bayesian optimal revenue. And second, we will try to adjust the revenue curve such that the equilibrium bit of the agent will going to be minimized, and correspondingly, the expected payment of the agent will also be minimized. This means that we minimize the expected revenue of the seller by adjusting the revenue curve. So by iteratively applying this adjustment, we will define the worst case, or at least approximate worst case distributions for maximizing the prior independent approximation ratio. Note that in the analysis, we have to divide the analysis into several cases, and in some situations, bounding the prior independent approximation ratio is hard. In that situation, we would find proper upper bounds for the prior independent approximation ratio and find the worst case for those upper bounds. Okay. And by just analyzing those worst case distributions, we can actually see that by setting parameter alpha equal to 0.7, the prior independent approximation ratio of the sample band mechanism for regular distributions is at most 1.835. So far we have seen that non-revelation mechanism actually performs well in this prior independent analysis. But exactly how much better can they do? Can actually non-revelation mechanism achieve spatial optimal, even if the seller doesn't know the distribution? So the answer is no, just by considering the family of uniform distributions, which also include degenerate point mass distributions. Okay, the intuition is as follows. Suppose that the maximum can actually achieve spatial optimum, then when the true distribution is uniform distribution supported on between 1 and 2, then the optimal maximum has to sell the item with probability 1 by charging the agent with price equal to 1. However, if that's the case, when the true distribution is just a point mass with supported on V, which is strictly greater than 1. The seller doesn't know this, but the agent knows. So agent could just simulate the bidding strategy as if it's in the world of uniform distribution. then the agent would actually win the item with price just equal to 1. This means that the revenue of the seller is 1, which is strictly less than the optimization revenue, which could potentially be V, that is strictly larger than 1. So this illustrates why we cannot exactly achieve spatial optimal. And essentially by leveraging the tensions between those two cases, we can show that even for uniform distributions, the prior-independent approximation ratio for any mechanism should be at least 1.073. So now that we have seen for the non-reversion mechanism, what about revelation mechanisms? So for revelation mechanism, we would be interested in the sampled place pricing mechanism, which is essentially just posting a take it or leave it offer to the agent with some possibly randomized price. And the agent will decide to accept it or not after seeing the price. And in our paper, we actually show that in this prior independent framework, any revelation mechanism is essentially a sample-based pricing. And the next paper by Alo and Bursworth shows that actually they provide the prior independent approximation ratio bound for the sample pricing mechanism. And combined with our lemma, we can actually show that the prior independent approximation ratio for any revelation mechanism for the amateur distribution is just roughly 1.5, and for regular distributions, it's just roughly 1.9. And finally, to summarize our talk, this table illustrates the known bounds on the prior independent approximation ratio for both the revelation mechanism and the non-revelation mechanism. And combine those results, we can show that actually in the single item, single agent auction, when the seller only have access to a single sample, for revenue maximization, the revelation gap is bounded as follows. And the main takeaway I want to say is that this result stresses the importance of analyzing the non-revelation mechanisms. Although it's theoretically challenging, we can see that actually non-revelation mechanisms are widely adopted in practice, and moreover, in some situations, non-revelation mechanism can give us strict beneficial compared to the revelation mechanisms. And finally, I would like to talk about some potential open questions following our work. Note that in our paper, we have illustrated the revelation gap with some regularity considerations and shows the revelation gap is bounded within some constant. Is it possible to find any super constant revelation gap for this single sample setting when we drop the regularity assumption? And another interesting question is to find whether a revelation gap exists for the multi-agent setting, for example, the digital goods setting. Note that traditionally, what people have been done with digital good is to use other agents as samples for another group of agents. And note that for non-revelation mechanisms, those samples are actually base samples, which is in contrast to what we have done in this paper, which is using valuation samples for designing the mechanism. And finally, an interesting question to ask is whether a revelation gap exists for bilateral exchange setting, where the objective could be maximizing the welfare or maximizing the gain from trade. And that's all for my talk. Thanks you for attending.